arithmetic series. We know what an arithmetic sequence is, simply a list of numbers that have a common difference. We can talk about a finite sequence or an infinite sequence. Here we see a finite sequence, 6, 9, 12, 15, 18, simply listing 5 terms of a sequence, and it stops, finite. We also see below it an infinite sequence, comma, dot, 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 ellipsis, meaning this sequence will go on forever, this list of numbers. Now let's talk about a series. A series is when we add up the terms in a sequence. So here we have a finite series, 6 plus 9 plus 12 plus 15 plus 18. Can I get the sum? Yes. Adding those up, it equals 60. That's in a finite series. Let's find the sum of the next series. Well, let's see. 3 plus 7 plus 11 plus 15 plus dot, dot, dot. This is an infinite arithmetic series. Can I add it up? It doesn't end. So no, there is no sum to an infinite arithmetic series. As we saw above, if I have a finite arithmetic sequence, I can find the sum of the series. And when I have just 5 terms, not too bad. But what if I have a ton of terms and I want to add them all up? Well, let's look at our first example and then we'll come back and see if we can figure out the formula. What is the sum of the first 50 even integers from 1 to 100? Okay, first of all, let's determine, is this an arithmetic series? Well, the first even number is 2 plus 4, because we're talking even numbers, so 2 plus 2, 4, plus 6, plus, and so on, plus, what's the end of this series going to be? Well, 96 plus 98 plus 100. All right, do you want to pause and see if you can figure out the sum of the first 50 even integers from 1 to 100? Okay, I find this very interesting. Let's look at some sums of our series. Let's take our first term and our last term. 2 plus 100. Well, that's 102. What about our second term in the series plus the second to the last term in the series? Well, that's 4 plus 98. That's also 102. What about the third and a third to the last? 6 plus 96, 102. Is that enough to convince you that we're going to continually get these pairs that add up to 102? Now all we have to think about is how many pairs do we have? Well, there's 50 terms, so 50 terms and we're pairing them up. 50 divided by 2, 25 pairs, and the sum of those pairs is 102. So without worrying about notation here, we know that we have 25 pairs and those pairs add up to 102. 25 times 102 is 2,550. Way easier than sitting there, even with a calculator, going 2 plus 4 plus 6 plus 8 and so on. Let's use this example to formalize and develop a formula that we can use for all arithmetic series, finite arithmetic series. I started out by adding the first and the last term. Now, the last term number will change depending on the series. So I'll just say a sub 1 plus a sub n, meaning the last term. That gave us 102. Next, I had to decide how many pairs I had. Well, the total number of terms was 50. And because I'm making pairs, I divided by 2. So our formula will be number of terms divided by 2 times the sum of the first term plus the last term. Pretty cool.
Let's find the sum of a finite arithmetic series given a sub 1 is 9, d equals 7, and n equals 68. Oh, n equals 68? That means we'd have 68 terms. We don't want to do that by hand. Good thing we have the formula. I know I'm going to need n, which I have. I also need a sub 1, which is my first term, and a sub n, that's my last term. I don't have my last term. How could I find that? How could I find a term in a series? Remember last lesson, explicit definition helped us find any term we wanted in the sequence. Well, I could use that. Let's recall the explicit definition. It's a sub n equals a sub 1 plus d times n minus 1 for n greater than or equal to 1. Well, a sub n is going to be my a sub 68. A sub 1 is 9 plus d they gave me is 7 times n minus 1. Wait, I know n, it's 68, so times 68 minus 1. Well, if I evaluate that down, I'm going to get a sub 68 is 478. So that means my last term in the series is 478. Now I can plug it into the sum formula. S sub 68, the sum of those 68 terms, is 68 divided by 2 times 9 plus 478. Well, now I can plug that into my sum formula. So S sub 68 is, pull out your calculator, be sure to show your steps. S sub 68 is 16,558. Take a look at the next one. What do we know? What do we need to find? So what am I missing this time? N. I know the first term, I know the last term, but I don't know how many terms I have altogether. So how are we going to find n? Explicit definition. Let's plug in what we know of the explicit definition to solve for n. I know the last term is 99. I know the first term is 4, plus I can see that the common difference, d, is 5. Now I can solve for n. Did you get n equals 20? Did you find it a different way? That's okay. Now that we know all the pieces, go find the sum. Look, our sum is 1,030. So looking back at these two, anytime we're missing something in our sum formula, we can just use the explicit definition to find it.
To represent series, we need a more concise notation. We use summation notation. It utilizes the Greek capital letter sigma, a big E. For example, we see the series 3 squared plus 4 squared plus 5 squared and so on. The argument for this series is n squared. N squared represents the terms of the series. The first term starts with n equals 3. This is the lower limit, and we end with 108. That's the upper limit. If we start with n equals 3 and go to n equals 108, how many terms are there? Are you tempted to say 105? Let's think this through. If I assign you problems 1 through 5, how many problems do you have? 5 problems. What if I assigned you problems 3 through 9? Are you tempted to say 6 problems? Let's count it. Problem 3, 4, 5, 6, 7, 8, 9. We have 7 problems. So if you're going to subtract, you have to account for that first problem. So 108 minus 3 is 105, plus 1, 106 terms to this series. Let's look at an example of summation notation and see if we can expand the series. This time our argument is x to the power n divided by n factorial. Our lower limit is n equals 2, so we start with the number 2, and we go up to the upper limit of 5. So summation notation says that I would add all terms x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4th divided by 4 factorial plus x to the 5th divided by 5 factorial. You can see that summation notation is a much more precise, concise way to show a series.
What are the sums of these finite series then? Are they arithmetic series? Well, looking at this first one, I could start to write out all the terms. Looks like my lower limit is n equals 1, so I'm going to start by plugging in 1 to get my first term of -5. For my next term, I'm going to just plug in 2. Then I'm going to plug in 3. Oh man, I'm only on term number 3 here, and I'm supposed to get up to 40? There's got to be a better way. Well, is it arithmetic? Because if it's arithmetic, I can just use the sum formula. Let's check. I could look at the series I've written out so far, -5 to -2, I'd add 3. -2 to 1, I'd add 3. So that's seeming like I have a common difference. But hey, if I look at the argument in my summation notation, 3n minus 8, well, that's linear. Well, if we think about the explicit definition, they're always a linear equation. So this must be arithmetic, and I can use my formula. All right, well, to plug into my sum formula, I'm going to need to have n. N is the total number of terms. If I start at 1 and I'm going up to 40, do I just have 39 terms? 39 plus 1, so I have 40 terms altogether. a sub 1, so that's my first term. My lower limit's 1, so I'd plug in 1, I'd get -5, so my first term in my series is -5, and then a sub n is a sub 40, because there's 40 terms. Well, I already found that by plugging in 40, got 112 as that last term in the series. Let's plug into the formula, see what we get. And look at that. Using the sum formula, I have s sub 40 is 2,140. Oh, and we didn't have to find that by hand.
Looking at this next series, is it arithmetic? Can I use my formula? Oh, the argument is n cubed. Well, that's not linear. Ooh, what would I do? How many terms are there? It goes from n equals 1 lower limit to upper limit of 4, so I have 4 terms. Whew, thank goodness, I can just do this one by hand. So plug in 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, and find the sum. The sum is 100. Let's take a look at the next one. Gosh, I hope it's arithmetic because it goes from lower limit of 0 to upper limit of 100, and that's 101 terms. I'm not writing all of those out. The argument is -1 to the power n. This is exponential. This is not an arithmetic series. I can't use the sum formula. Well, let's start writing some of these out and see if we see a pattern. So -1 to the 0 power. Anything to the 0 power is 1. -1 to the first power, well, that's -1. -1 squared, -1 times -1, +1. -1 cubed, -1 times -1 times -1, that's -1. Okay, I'm starting to see a little something here. -1 plus 1 is 0. 1 plus -1 is 0. They're adding out. Is my sum 0? Our last term is going to be -1 to the 100 power. So is that getting paired up to make a 0, or is that an extra? Let's look. I plugged in the lower limit of 0 and added it with the next term where I plugged in a 1. That made a 0. Okay, then I plug in a 2 and add it with plugging in a 3. That made a 0. So every time I had an odd exponent, it added to 0. That means -1 to the 100th power is an extra. So following that pattern, -1 to the 98th and -1 to the 99th would add to be a 0, and -1 to the 100 would be left over. Well, -1 raised to the 100th power, -1 times -1 makes a +1, and so on. The final answer is 1. Next, we're given a series and we're asked to write it in summation notation. Well, we're going to need the argument. Let's see if it's an arithmetic series. Remember how we check? Term minus previous term, so 11 minus 7 is 4. 15 minus 11 is 4. 207 minus 203 is 4. So we have a common difference of 4. Let's plug into our explicit definition and get the argument. The argument for our summation notation is 3 plus 4n. Now we need to get our lower limit and upper limit. Well, lower limit, let's see if 1 works. If n equals 1, then 3 plus 4 times 1 is 7. That's our first term. Now let's get our upper limit. We can use the explicit definition that we already have in order to find the upper limit. We know the value of the last term is 207, so I'll plug that in for a sub n and solve for n. The upper limit is 51. Now it's your turn to try. A good place to start is seeing if it's an arithmetic series. If it is, then you can find the explicit formula and go from there. So checking term minus previous term, term minus previous term, we notice that there is a common difference of 7. Next, we find the argument by writing the explicit formula. So a sub n equals -12 plus 7n. The lower limit, n equals 1. Quickly, I can check that. -12 plus 7 times 1, -5. But the upper limit, I need to plug into that explicit formula and find out what that upper limit is. The upper limit is 40.
Now a quick review to check your skills. What is the sum of the series? Pause, try both. Let's check the first one. Did you look at that one and see that there's 70 terms? I sure hope it's arithmetic. It is, since that argument was linear. Since it's arithmetic, I'm using the sum formula. I need n, a sub 1, and then a sub 70, since there's 70 terms. Once I plug into my sum formula, I get 12,635 as my sum. Checking the second one, it was not arithmetic, because that argument's not linear, it's quadratic. Luckily, we only have 7 terms, so I can start at that lower limit, plug in, and add them up. The sum is 91.